No one's speaking.
Hello, can everybody hear me? Let's see. I'm
Yep,
basically,
okay.
okay, good. I'm basically testing a new microphone today because last time somebody said that there was some bad signal and it was like underwater or something. So I was trying to figure out what it was. So I have now a new microphone and I'm trying to see if that's going to be better. So let me know if it works for you or not. I think the other possibility for the bad sound in the first week of the lectures maybe was because I'm just trying to fix the microphone, sorry. Some students maybe signed in later and maybe that the algorithm picked up the sounds and changed something temporarily. Or maybe it's because of the servers, being different distances apart or something like that. I'm not sure, but we'll see how this goes, this lecture. So if you can, please turn off your microphones. I'll keep mine on so we can record this lecture. I'll check if it's recording. Yep, it's recording. So I will start sharing my screen now. Yep, okay. So this one here. All right. So can you see it?
Yep, I can say that.
Thank you so much. Okay. All right. So let's turn off the microphones, please. And I will start the lecture because we are now 5 minutes past 2. And I think everyone should be already here now. Okay. So I will zoom this larger. So we will continue from the last lecture where Professor Feng Liu left off. And it was on the multidimensional optimization. So in particular, he was talking about the steepest descent method, and then you discussed basically how to calculate the gradient and the distance to the next point along that gradient, and then how to actually step to that solution of the global or local minimum, and you could use also a graph to represent this stepping procedure. The method was a bit slow, if you remember. It took several steps, and therefore we'll be looking at Newton's method, which is a bit different method, better method compared to steepest descent in many regards. And we will discuss the details of that method, as well as conjugate gradient descent method, which is a little bit similar to the descent method with some twist to it. So it's a very popular method in engineering. And so CG, we will discuss with some examples as well. And then we will also talk about the Gauss-Newton method as the last method. And then in the next week lectures, you will have probably, I think, 2 or 3 more methods, and that will be it for this semester's optimization course. All the theory will be presented in that regard, some examples, and then you have a chance to study these tutorials and then to program it as well. And I will show you some examples at the end of this lecture. If we don't finish everything this Monday today, I will then finish off some parts of it on Wednesday, and then continue on Wednesday with least squares. We will study least squares on Wednesday, linear least squares, by the way. Okay, so Newton's method. So as we saw previously, the steepest descent method was slow to converge. it takes a large number of steps to reach the minimum or maximum. And if you remember from that graph, you're stepping through that search space and it takes a long time. It's a bit inefficient. So Newton-Raphson is the other method which you'll be looking at, and it's an effective way of finding the roots or solutions to the problem. And it can be adapted to also finding extrema, which means, global minima, maxima and such. And the Newton method is based on Taylor series approximation of the function fx. So if you remember from your 1D optimization, you had the Taylor series expansion of a function fa plus h. So we have a point at distance a from origin called k. So we have a value at that point called f of a. And if we then want to compute some distance h, or call it delta x or something like that, so this is h away at point fa plus h, we can actually approximate this point, this value, by Taylor series approximation as shown in this formula here. So that point, the next point would be the value at the previous point plus the distance h from that point, or the distance, multiplied by the first order gradient or the first derivative of f evaluated at point A, plus h squared over 2 factorial second order derivative at point A, and so on until nth order derivative or nth order gradient multiplied by this coefficient here, which has n factorial, which means n times n minus 1 times n minus 2, etc. So basically here we have just 2 times 1. So this factor, it will be just 2. That's very simple. And in general, you would have this expression if you substitute, as in maths, we always use x to represent any value, not just a. You would have this expression here, which is identical just with x instead of a. And because in engineering or in real world, we cannot simply sum to infinity, there's too many terms, we have to truncate it somehow. We have to also simplify the problem to be computationally efficient. So we have to just take some terms, maybe first, second term, or maybe up to the third term. So typically what is done is maybe the first 3 terms are taken, that leads to a good approximation. And later on, we will see that actually also leads to a reasonably good solution finding, and it's efficient as well. So it's a compromise that you have to take. So in this case, we would just take the first 3 terms, and the last term is the second order gradient, which needs to be computed. Often this gradient here, the second order gradient, is a little bit computationally intensive to compute. We will see some ways to actually use some mathematical tricks to avoid using it if we can. Sometimes it's unavoidable, but let's say this is just what we want to use. So now, if we look at this slide here, this is basically the representation we just saw just a moment ago with the one-dimensional Taylor series expansion. But in this time, what we have here is a multidimensional expression. So if I actually, let me just zoom out of this slide so I can show you what this looks like from here. Okay, so if you look at this fx plus h here, right? Or fa, assume it's a, okay? So we have a instead of x for this expression here. So we have this term here, f of a first. So we have f of a1 up to an. So that's straightforward. We have multiple parameters to optimize in the multi-dimensional case. This is not one-dimensional anymore. It's now multiple parameters. So a1 to an. And we also have this hf derivative or first order gradient of x. We can express this by h transpose. So this is the vector h, but we transpose it because we want to multiply with another vector. So because it's also multiplication here, we can represent this as also dot product or multiplication here. So this would be transpose vector times this vector, and it leads to a solution. Otherwise, if you just have h times g, that would not work mathematically in terms of matrix form. So this works out, okay. So this g here is nothing less but a vector of derivatives or the first order gradients of f at x. But now we have derivatives at x1 up to xn, because we are, or in this case, it's a general case, or you can say a1 to an, you know, it's just a presentation, basically, this general case. So we should put probably here x. So maybe I can check with the cross coordinator if we should change this to x. So this is all consistent then, you know, but you get the idea, right? So this is the idea. So now you have this vector and h, this is transpose. So it's horizontal multiplied by this and the second order term. Now the 2 factorial evaluates to be just 1/2, right? And h squared, we can write this as h transpose times h, so that each cell element can be multiplied with the other cell element by itself. So it's like an inner product kind of. So this is h transpose h, which then leads to that h squared, and j is the big square matrix, because we are now taking into account a second order derivative. And if you take second order derivative of this, let's say, take the first order derivative of this one, eventually you will see it actually comes out to be a square matrix, J, and it contains second order derivatives, as you can see. In the first row, they are all in terms of, in the first column, they're all in terms of x1 here. So there's partial derivatives in terms of x1, but also the second row would be dx1, dx2, and then dx1, dx3, etc., and up to this term here. But in the end, it just comes out to be dxn squared. So this is the form of that matrix. There is a very simple expression that we will see in next slides, which you can easily remember, and then you can actually write these yourself. And it's very straightforward to actually express it if you remember just one simple formula, or you can read it from a book. Of course, you don't want to always remember this in future in engineering practice. You will go back to, you know, internet or book and just find the, oh yeah, this is the form, and then you express it. At least you know what you're doing. You know the problem, you understand what to solve for, then you can just find it and do your maths, right? So you don't have to always remember everything, but maybe for the moment, maybe in the final exam, there may be a formula for you there, or maybe you have to briefly remember what it looks like. We'll let you know probably before that time. So otherwise, yeah, this is the form. So you have H transpose JH. Now this matrix here, I will now zoom up. This matrix here is called a Hessian matrix. It's a square matrix containing second order partial derivatives. They're all partial, by the way, so there should be a different sign, yeah? Just the lecture notes I got. So, but yeah, so this would be second order matrix. So we have H is a column vector, and then G is a gradient vector, and this is sometimes called Jacobian. This G is called often Jacobian, and second order is called Hessian. First order is Jacobian, second order square matrix is Hessian. This is the mathematical terminology used for over 100 years now, maybe. And this is the form, yeah. So this is what we need to actually work from now in multidimensional optimization problems. So in the Newton's method, what we use is a quadratic Taylor series expansion as the approximation of the objective function f. So let's say you have objective function f, you want to actually solve for, to optimize some real world problem. Then you express it as a Taylor series approximation, the general formula. You take some of the terms, maybe up to the second or third term, and then you actually do the other approaches like Newton's method or whatever else you want to do. And then you find the maximum or minimum of this approximation. This often involves one way, the simplest way, as you remember from your high school mathematics, is that you take the, from the expression that you derive from that objective function, you take the derivative of that function or the gradient and set it equal to 0. That solves that problem to finding a maximum minimum point. So if you have a square function like x squared plus 2x plus 3, you solve x squared plus 2x plus 3, taking the gradient, so it becomes like 2x plus 3, and you set it equal to 0. that finds you that point where there's a minima or maxima, then you have to take the second order derivative to find which it is. Is it a minimum or is it a maximum? What do I have? What extrema? So then use second order derivative, right? So this is the very basic stuff from high school. But here, this is how it's done. And then the next step is to step to this value, this function to actually numerically step through. And then you actually converge to a solution, final form. As you saw with the steepest descent method, and you also looked at things at Gordon section and the parabolic approximations and such, there's a convergence criteria. So you can see how the algorithm starts to converge to a particular point where the solution does not change anymore. So you then have to check, am I finding here a local minimum or a global minimum? Am I trapped somewhere in a non-optimal solution which tells me it's optimum, or am I somewhere which is really good? That's another question entirely later on when you study. I think next few weeks that will be maybe looked at a bit deeper. So now if we have the Newton's method and we want to then optimize for the solution, we can, for example, set it equal to 0, the first derivative, let's say. And in this form here, so what we're doing is just setting the partial derivative. Oh, well, yeah, so it's a hi, but let's say the first term would be 1. The other ones, in terms of dh1, would be all 0. So we're looking only at dh1, let's say. And it's not well written here, I can see now. So I think this was, yeah, I'll check with if we can amend it. But actually, yes, this is just this form and times g. And then this part here, as you will see in next slides, how this comes about to be, that the two terms happen to be here. It comes from a product rule from differentiation. So if you have, let's say, x squared times, let's see, like exponential of x, you have two parts. You have to then, if you take the derivative of that, you have to take derivative of each part separately, and you get two terms. So I'm going to show you that a little bit later, or by example. So basically, we'll see how this comes about in the next few slides. But in general, this is the expression here where we have again just 1 in front and so on. So let's go to the next slide. I'm gonna zoom out to show you the difference. So okay, so here, so as J is symmetric, so for any vectors R and S, mathematically there's an identity that can be written, let's say R transpose J times S, S equals to the same expression transposed. Its equivalent equals to now S is transposed and R is not. So basically we flip them and change the transpose. So this is identically true. So if we assume that this H here, this H transpose is R transpose and this vector here is S, then basically it's also can be written as that vector transpose in front and the H becomes here. So basically you can flip this around. So what you basically get is you basically get a JH, right? So here you get same expression and then JH, and then you have here same thing, JH again. So this is pushed in front, so this becomes this, right? So this vector S comes to front, becomes transpose, so it becomes ST, and this part here, HT, becomes just H on the other side, just like R here, right? So what you get is same thing again. You get exactly the same thing again here. So this here becomes identical to this. It's exactly the same. It becomes 1/2, and then this vector JH. So this is then 1/2 of that plus 1/2 of the same becomes just that, right? This part. So this part here just remains as 1 times this part. So you get just this G times JH, and you factor out that common vector in front, which say S or something. You factor it out. So this is how you I'm just, you don't have to, I guess, go into details remembering this, but I'm just showing you how they mathematically arranged it so that they can derive this formulation. So that this can be seen in terms of simplified form after the derivation of df/dh. So basically, you will have multiple df/dh1, df/dh2, df/dh3, etc. So there's multiple of these derivatives and set to 0. So the only way to satisfy this solution is if this g plus jh is 0. So no matter what we have here, we have to have something on this side to make this 0. The only way for this to happen, as you can see, is if this is 0. So if this is 0, then this is all 0 then. And therefore, this is a satisfied condition, g plus jh equals 0. If we bring the g on the other side, it becomes negative g on the other side on the right-hand side. And we just then have a solution g of gh equal to minus g becomes inverse of this matrix. Take the inverse. This is the formula ax equal to b. If you remember, and x equals to a inverse b. This is the solution, right? So this is how you solve it. Very simple, as you remember from your maths. And if you remember now, if you go to your 1D case of Taylor series approximation and Newton's method is very similar to that. You remember you saw there was h equals to negative first order gradient over the second order gradient. This was the expression formulated last time, probably like in the last lecture set for the 1D case. And this was the next stepping point. So x at k plus 1 is equal to x at point k plus h. So this was just Taylor series approximation. But here you can see now we have same thing. It's just that we have a matrix formulation, and it's very similar. So if you look at G, you know that it's very similar to F bar, the first order gradient, and J, in this case Hessian matrix, is a second order gradient, F2 bar. So in the denominator. So this here is inverted. So it's kind of like in the denominator, if you think of it, right? So you have now basically a at point I plus 1 equals to a at ai, so the previous point, plus h. And then you can substitute for this h in here, and you get minus, so ai minus ji inverted gi. So this is the expression. This is the next point to calculate. This is what we want to step through and evaluate. So as you can see, the multidimensional case is just an extension of the one-dimensional case you saw previously, but written in matrix formulation. Nothing different in terms of philosophy of it. Okay, so what we want to do is repeat with the algorithm how it works. We start with oh, sorry, microphone, somebody. Please turn on the microphone. It could mess up a little bit our sound here. Hello? Somebody has a microphone. Can you please turn it off? Thank you so much. Thank you. Okay. Right, so we got to repeat AI, which is known. So the first point, we have a starting point, which we want to use as an initial guess. And unfortunately, even here, we have to start very close somewhere to the final solution, not too far away, because just like in 1D case, Newton's method, it's not that good at finding solutions. If it's too far away from the solution, it can get stuck somewhere else, and it's not going to work always. So yeah, so otherwise, the calculation is that we calculate the gradient with the first order derivatives, and the other one, the Hessian matrix, with second order partial derivatives. And then we calculate this formula here. This is the formula. This is the main thing we want, this here. So, and we want to actually step until sufficient accuracy is reached. So to see an example in action. So let's say we have here function as used before in the last lecture set, where f of x is x1 squared plus 3x2 squared. we have two parameters, x1 and x2. These are the unknowns, right? And we want to start at some point 6, 3. Call it whatever you want, y0 equals 6, 3 or whatever. So in this case, just call it x1 or something. But it's not actually x1, so it's like just a point. So 6, 3. So we have here the first, to calculate the g, we have to calculate, of course, the first order derivative, so df dx1. So if you differentiate this in terms of dx1, so you only this part here counts. The second part doesn't have no x1 here, so this becomes like a scalar. So you can treat this as a number only. And this one here is now 2x1. So you have 2x1 if you differentiate these. And then the second one is in terms of dx2, so df dx2. And only this term has dx2. The other one falls out. It's just like a scalar. And now we have 2 times 3 is 6 x2. So we have x6 x2. And then we also want to now differentiate second order derivative in terms of dx1 itself. And the only way to do that is to take the derivative of derivative itself here. So we can just look at this form, take the first order derivative of the first order derivative to get the second order derivative. So basically we applied here. We see it's 2x1. And in terms of dx1, to differentiate these, it becomes just 2, right? So this just becomes 2. But this next term we want from the Hessian matrix J is this term here, which has dx1 and dx2. And if you look at this form here, so d squared f df second order derivative of dx1 dx2 is, see this term here is same as here. In terms of dx2, there's nothing here in terms of dx2, right? So there's nothing here in terms of dx2, which means that this is 0. So there's nothing here, it's just a scalar. And same thing here. So, and you go on. So once you check this, you see that dx2 derivative is 6 and then 0 here. So this is the first term, this is the second term, this is the third term, and this is the fourth term. And if you write the expressions for A, it's just 6, 3, this point here, 2 parameters, 2 cell entries. And then G is just this 2x1, 6x2. If you evaluate by substituting our initial guess point 6, 3 into here for the initial guess, you will get 2 times 6, 12, and 6 times 3, 18, just like this, right? So this is the expression we want for this point. And then we have J, so that Hessian matrix. So the first term is 2, second term is 0, and this is the final term. If you remember, it's dx2 squared, so dxn, so it becomes here. So it's 6 final entry, and this is 0. So this is the expression. And if we go to calculate the matrix inverse, I guess I'm just gonna write here because nobody wrote the lecture notes, it seems. So if I can find how to annotate, okay, here annotation, and then I can use drawing tool, right? Okay, maybe I can use drawing tool. Okay, so okay, from my top of my head, I think it's just like okay, so you have a matrix, right, of elements A, B. I'm writing with my mouse. Maybe I should get like a proper set of writing tools for this. So it's you have a matrix A which has this form, right? So, and then it will be the determinant of this multiplied by the modified form of that matrix. So it's A times D minus B times C. This is the determinant multiplied by this expression here. And so if I remember from memory, correct me if I'm wrong, but this would be the form if I remember. So if you, this would be the matrix inverse of that for a 2x2 matrix, by the way. So we're talking only about 2x2 matrix. And so if you multiply A times D, so what was it? 2 times 6, right? It's 12 minus 0, and that's 12. And then here we have, this is 6, this is 2 from memory, right? This is 0, this is 0. So if you then multiply it out, you will get this expression here. So it's 1 over 12 times 6, it's 1/2, and this is 3. So 1 over 12 times 3 is basically 1 over 6. So it matches correctly. So this is how we calculate 2 by 2 inverse and get these values, right? And then we can calculate the new step. But otherwise, by the way, if this was a huge matrix, like millions and millions of entries, right? So million by million at same size, you would have to use something else entirely to calculate this. There could be many ways to do this. One of the ways could be using maybe pseudo inverse, or you will do the computer, of course. You won't do it by hand if it's huge. But there's many tools to calculate the inverse of a matrix if you are just doing it on a larger scale. This is just a 2 by 2 case. We can just do by hand, right? Okay, now if you want to calculate the new point, a k plus 1 or a nu, it would be just that previous point a minus, if you remember the formula we used, inverse of j, right? And this would be this one, multiplied by g. And g is this, right? At point A, original guess. And if you multiply this out, so 1/2 times 12 is 6, 0 times 18 is 0, so that becomes 6. So this result of this first multiplication is 6. 0 times second term is 0 times 12, 0. 1 over 6 times 18 is 3. So that's 6 over 6 and 3, right? 6 and 3 minus 6 and 3 is 0, 0. And we have a next step, right? But we know from previous example from last lecture that this is the solution already. 0, 0 is our global minimum. So if I go next slide to show you that, I'll just quickly delete, clear all drawings, right? If I go to the next slide to show you, this would be represented by starting point 6,3. As you can see here, x is 6, x1 is 6, x2 is 3, and it just steps straight to the minimum. There you go, done. This is pretty cool because we already found the global minimum for this simplified, very simple expression of that, what was it, x1 squared, 3x squared, 3, yeah, x2 squared. Very simple formula. So in this case, it leads to an exact solution, maybe because simple formula and Taylor series expression, we use second order derivatives and such, and it just gives the roots immediately. So we have a solution immediately. For more complicated formulations, this may not be immediate, of course, but this case happens to be straight. See, this is so much more powerful. Let's say now if you compare it to the steepest descent method or parabolic approximation and such, or parabolic optimization or steepest descent, it's one step only, which is pretty interesting, right? So right, so this is the main message. This is the expression we want to evaluate until sufficient accuracy or convergence is reached. First order derivative made this vector here, and second order square matrix J containing second order partial derivatives. Yeah, so this is the main formulation. And we see just example here how this works. All right, so now, I guess it says here the broader view can be obtained by local quadratic approximation, which is equivalent to Newton's method. And in the multidimensional optimization, we seek 0 of the gradient. So just like in the one-dimensional case where we saw 0 of the gradient, we take the partial derivative of the function set equal to 0 and solve for it. We find that minimum point. And the Newton iteration in this case for one-dimensional case is simply this. Next point is the previous point minus that Hessian. So now this is the proper way maybe to write it. Sometimes it's written by H instead of J. So this is H goes Hessian matrix. Previously I wrote it's J, but often you also see this H. And the gradient G is nothing more by using green operator, inverted square right triangle here, times f at point x. Okay, so this at this point here. So this is G, this is the previous J inverted. So yeah, so inverse of this is the Hessian matrix. This is the formula which I told you how you can actually express and write out the full matrix H, or J previously seen. Now we can call it H. This is much easier to remember, and we can easily differentiate H from J, because sometimes J is reserved for Jacobian matrix. Sometimes it's used called Jacobian, which is the first order derivatives. So we can differentiate them by calling this H. So, and this is the formula. So partial derivative of f of x, or second order of f of x in terms of xi and xj. So if you want, and this here is expressed this form, right? So ij points. So these are the rows, these are the columns of that matrix. This is a matrix now. So if you write it down, you would get that previous expression I showed you, where you have I rows and j columns, and this is the formulation. So you can actually write by hand, and very easy to express now. If you just look at the big matrix previously, if you look at this crazy thing here, it's hard to see what's going on, right? Very hard to see. But if you look at this formula, yep, now you can write it down, right? So this is how it works. Okay, so this is the main message. The Newton's method is derived this way. And we have H instead of J, just for the convenient sake of naming it something more convenient, like a Hessian matrix, which is what it is. All right, so sometimes it's actually very difficult to find this inverse of of that Hessian matrix. Maybe there is no inverse. Maybe it's very hard to find. Maybe the matrix is ill-conditioned. It's underdetermined. It's very large. It contains lots of noise or something. It's maybe nightmare to find the inverse. So sometimes there's other ways to solve it, as you will learn in the next set of lectures in the coming weeks, is that you sometimes can express this function, this expression previously, this one here, by just imagine bringing xk to the other side, left side of that equation. You would get xk plus 1 minus xk, right? You can call that s of s, this one, s, right? And then on the other side, all you have is negative h inverse times the gradient. So basically, if you then also bring the h to the other side, it becomes this. The inverse goes away, and you're left with this matrix h times s. Now, both k plus 1 and xk are gone, because you convert them to s of k, and where we have here that s of k is equal to xk plus 1 minus xk, so it will be on the other side, so you can substitute it, and this is how you get. So if anyone has any trouble, I can write it down by hand, but I'm pretty sure you can see it, right? In this advanced course, we should be able to see it. So it's actually, yeah, straightforward. You can actually just see that this is sk is xk plus 1 minus xk, and you can substitute by rearranging here a little bit. So then what you have is this formulation. So if you have this formulation, you can actually now do some, you can solve it in different ways. As you will learn in the next set of lectures in the coming weeks, is that these can be solved in different ways without taking the inverse. Excuse me. All right, so, and we won't go into details here, but I'm just telling you that sometimes this can be conveniently used without taking the inverse always. This is just another way to actually solve it. And so the convergence rate of the Newton's method for minimization is normally quadratic. And that's good because it's faster than steepest descent method, being quadratic. And Newton's method is unreliable unless started close enough to solution to converge. Just like in 1D case, you have to be not too close, but reasonably close to the final solution in order for this to converge. Otherwise, it might have trouble converging. And so that's one message we have from this here. So what's the time? Okay, I have to, I guess, hurry up a little bit. So Newton's method to minimize this function here. Let's see an example. In this case, we want to assume to use this kind of expression instead of the inverse. Let's say assume we want to solve it this way. So let's say we calculate the gradient first. Okay, so we have gradient of this function is just 2 times 0.5 x1, so just x1, and 2 times 2.5, which is 5 times x2, so we have 5x2. So this is the derivatives of these first order. So this is your you can call it big G. Here we have this expression. So this is the normal way of writing it sometimes as well. And H is this. So we let me see. So basically, so take the partial derivatives again. So for x1, partial derivative in terms of x1, dx1 is just 1. So this falls away. For x2, there's no x2 here, so just 0. And this is also no x1 here, so it's 0. And there is x2 here, so it's just 5. So this is how you get the Hessian. And then you express it in terms of, let's say, take the first guess. So let's say we guess it to be 5,1. This is the initial guess, 5,1. And we calculate this at guess 5,1. We substitute 5 here, it becomes 5. Substitute 1 here, becomes 5 times 1 equal to 5. So we have 5,5. So now we have the gradient and the Hessian. Now we can write our expression. Hessian times the S of k, or in this case, our S0. So we're trying to find S0 because we have x0. So S0 is our search direction, in this case, kind of. And this would be that negative of that gradient. So you have a negative sign. So you have to take negative of this expression. So it's -5, -5, right? So then the next step is x1 is x0 plus s0. This is how it works. So you have here x1 equal to x0 plus s0. The next point is the previous or the guess, so 5,1 plus, and now if we solve this by using some method you will learn in the next course set, but because it's just a 2 by 2 matrix, it's very simple. So we have 1 times s0 equal to 5 -5, and so that the first term is s0 equals to -5, and the other one is 0 times s0 equal to -5, and 5 times s0 equal to -5. So it becomes just 5 times s0 equal to -5. So this is, if you solve it, becomes just, the second term is just -1, so -5/5. So you can actually already see the solution by just looking at this. Kind of, you can do it by hand. It's very simple to calculate. If you express it by hand, you get 2 equations with 2 unknowns, and this happened to the second term happens to fall off easily because it's a 0, right? So it's very simple. So you get this solution. If you add them, you get 0, 0, which is again that minimum we found previously, right? And so this is the minimum anyway of this function. It has to be, because if we look at it, there is it's not offset anywhere from origin, and it has to be at origin. It's also invert upwards because they're positive sign. So the squares or the parabola is going upwards, this square function, and it's a 2-dimensional. So you have it's like a surface. If you think of it, if you plot in MATLAB, it's a surface curling upwards. Right. So this method converges very fast, but it can be very unreliable because sometimes in reality, what you have in our engineering programs is a huge search space contained by lots of bottlenecks, like lots of hills. So you might be trapped in some sort of local solution, which is not a global minimum. Sorry, excuse me, I'm coughing. Need some water maybe. So basically, you might get stuck somewhere else entirely and not be able to overcome that hill here, for example. So often, if you do start from a point which can converge, you will converge to the solution. Otherwise, you might get stuck somewhere else. And this can also be highly depend on noise in the system, let's say in some sort of electronic system or whatever problem you're solving. In reality, right? So whatever it is, you might get stuck because of noise, because of the way the data is sampled. You have to sample some data maybe. in reality, and so on. So there could be issues. And there's also saddle points, like regions of minima and maxima, which is where you get stuck. And so this can happen in high dimensional problems in reality. It's not uncommon. So there will be some way to deal with this, as you will probably go on to study next set of lectures. But in this case, we show you this method, the basics of it, and how it works, and how it can be extended to some more sophisticated formulations. So if you compare the Newton's method against the steepest descent method, it's much faster. And if it's faster than other methods, it also can mean it's actually not very robust, but it's very efficient. Slower is more reliable, usually, not always, but in this case, steepest descent takes like a long path to get to the solution, longer than Newton's method, but it could be a little bit more reliable, perhaps. So sometimes we can actually take advantage of both methods, positives. So if one is fast, the other one is reliable, let's say, we can combine them in a hybrid formulation, so to take advantage of both their individual advantages. And so this is what's sometimes done. And we might modify, let's say, Newton's method to achieve that. So, and the conjugate method, which is kind of based on the descent method, but it's not exactly the same, will be studied next. I will start it off so we can actually finish most of the material, but I will take a maybe small break at some point so you can take a chance to rest. Okay, so the conjugate gradient method, basically it tries to relax the Hessian matrix operation, because the Hessian matrix is usually very computationally intensive to compute. It's a second order partial derivative matrix. It's got lots of computations. You want to kind of avoid that, right? So the other method which can be used, which does not require explicit second derivatives, you don't have to calculate those, and does not even store any approximations of that Hessian matrix. It's called conjugate gradient method. And this is what we will study next. So CG creates sequence of conjugate search directions, implicitly accumulating information about the Hessian matrix. So it's actually inherent in its own formulation that it does so. And this is the good part about conjugate gradient. It's very popular. So for the quadratic objective function, conjugate gradient is theoretically exact after most n iterations, where n is the dimension of the problem. And so it's got good, basically it's saying it's got good, well, stepping to the solution in terms of efficiency. It's not taking too long, not too short. We can actually find very useful in practice. And it's effective for general unconstrained minimization as well. And this is unconstrained for sure. So to illustrate the algorithm, this is the main algorithm. I will step you through it now carefully and slowly so you can understand. So the first initial guess at x0 is some sort of vector, let's say, right? So we have initial guess, could be like 5, 1 or something, but let's just assume it's x0, that vector. And we calculate gradient of the function. We always want gradient, as you noticed. And we calculate at point x0, at this initial guess, and call it g0. Okay, so far so good, right? Then next step is we have something we conveniently call minus g0 for computational simplicity later on in the algorithm of pseudocode. We have this term here called S0. We call it minus G0. Okay, so this is the first step before we even do any for loops or stepping. Now we do a for loop at this point here. So we have done that. We have initial guess, we have the gradient, and we have something called like search direction, if you think of it, right? Negative the gradient. This is kind of like the descent method where you have the search direction, direction. So now for loop goes from 0, 1, 2 up to n, and n can be any number of steps you want, depending on your problem. You can set it to be 100 or 1000, depending on your convergence of your problem. But sometimes you can also internally calculate, am I converging to the solution by doing some extra evaluations, and then check if I reached a certain condition, then I will step out of this for loop and I will stop because I reached my solution, which is good enough, and I will stop, right? So this could be a different formulation. If it doesn't converge, it might go indefinitely, and you will be, have to stop it somehow else, right? So, okay, so then in this for loop, as you note, you have a 0 here. So therefore, any expression will start with initial guess, x0, g0, s0. So this will be taken into account implicitly now. So we choose to now, it's first step. So we call this here, well, this section here 2, is to choose parameters or vector alpha k such that it minimizes this function xk plus alpha k sk. So this one here is just like in the steepest descent method, where you have previous step or the initial guess plus alpha k sk, but here sk is a negative g0. You can replace it, if you think of it, becomes negative alpha k gk, right? Negative alpha k gk, because it's just a negative difference. So this would be your search direction and distance to travel on a line search, like in the steepest descent. So up to now, this is very similar to steepest descent method up to this point. And you have so to do this, to actually evaluate this in terms at function f, basically you would have initial guess minus alpha. Alpha is unknown, you don't know it, but you know x0, you know your initial guess. Alpha is unknown, you have to find it. And sk is known because you can calculate g and you can calculate gradient at point x0, which is known. So this is all knowledgeable. So you can know this. But alpha k is unknown, you have to calculate this. So you can actually plug this into the original expression. I'll show you maybe later on how you can do this, one example. And then you can find alpha k. Once you find alpha k, which is the distance to travel, you can find out the next point, xk plus 1, which is xk plus alpha k sk. So this would be the next point. Now you have xk plus 1, the next point. Just like in the steepest descent, nothing different. Now, this is the tricky part here. So you have to calculate now the gradient at the next point. Very simple. That's simple. At this point, it's simple. Just gradient at that point, right? So gradient of function at this point which you just calculate, and this is, you call it gk plus 1. And now is the unique part of this algorithm, where you have a parameter beta, and this parameter beta is basically these two vectors multiplied, g transpose g for that next point, at this point, g at that point, divided by g transpose g at the previous or the initial guess point, or whatever the previous point is. So if these are all evaluated matrices or vectors, actually vectors, and they are known, they're all known. So when this is calculated, you will get a number, a just single number like 0.56 or something like that. So, and I'll show you an example. So this is a modified gradient. So what happens is now you want to calculate that next s. So this is, now you have x, you have g, you have x, you have g here. What you're missing still is s, just like here. You have s0, but you don't have s here. This is the way to calculate that s of k plus 1, next point, is basically that gradient itself, negative that gradient, plus this beta parameter times previous xk. It's just that formula here, which is something that is derived specifically for this algorithm. And I think we didn't go into details how this is done mathematically. It's probably extremely long to derive it, but I think just here you can see it, how this compensation is done. It's basically compensating for the gradient based on the previous gradient. And it's a little like a compensation scheme going on here. And so this is called Fletcher-Reeves algorithm, this part here. And the alternative formula for beta k is just the same thing here. But the only thing we do different is we take this G transpose K plus 1 here and subtract from it GK and then transpose it then. Everything else remains same. This is another way sometimes that you will see in literature this used, and it's called Pollack and Riviere method. So this one here is sometimes also used, and it has different convergence, maybe performance, but it may be useful for some applications. But in any case, this is the beta parameter which is computed in this way. And the way this method is called conjugate gradient, the conjugate terminology is when you have transpose times itself. So it's called conjugate pair. So this is why it's called conjugate historically, because of this conjugation pair. And it's a very neat formula which does not, as you can see, does not include second order gradients. It's just first order gradients. And so now we can actually see one example of this, right? So here we have a conjugate method which has this for this function to compute, and this is 0.5 x1 squared 2.5 x2 squared. So take the gradient. So we have x1 5x2 just as before, and we have so actually let's stop here, take a 5-minute break, and then I will continue to finish off this method and show you how it's done. Okay, thank you so much. I will see you in I guess 4 or 5 minutes, and then I will continue from where I stopped here. Okay, take a little break maybe. Thank you so much. I'll be back also in 4 minutes or so. Okay, so I'm back. Hope you are as well. Hello? Okay, I think it's working, the microphone. All right. So can you hear me? Maybe just write something.
Yep, we can hear you.
Thank you so much. Thank you very much. Thank you. Thank you. Okay. All right, let's continue on so we can finish more material. So I guess, so that function fx being 0.5 times x1 squared plus 2.5 x2 squared, take the first order gradient would be 2 times 0.5, so x1, and then 2 times 2.5 x2, so it's 5 x2. So we have those two. We're taking initial guess at 0.51. Written here as transpose, I guess it's just expressed here. If you transpose it, it becomes vertical vector. And that's the initial guess. And then initial search direction is negative gradient. So S0 is minus G0. So far, it's this part here, right? Not part 1. And if you express this gradient at 0.51, it becomes, I guess, substitute 5 here and 1 here. It becomes minus 5 with negative sign in front, of course, shown here. And then to find the exact minimum along the line, okay, so maybe I'm gonna write a little bit here to show you how I did it myself, but okay, I'll put here like this. So let's say let's see if I can use the drawing tool. Okay, go ahead. Okay, let's see if I can do this. So you have this 0.5, right? So first of all, we have that at x, what was it missing? Xk, sorry, minus alpha k, and then you have that S0, right? So something like that. So basically, or plus. So basically what you do is you substitute, so let's say it's negative G, right? Gradient. So you substitute these into the formula. So you have here 0.5, and you have the first part would be at 5, 1. So the first term is 5. You substitute this formula here. So you plug it in. X1 is, the first term is 5 from that initial guess, minus, and then this 5 from that other matrix. So you can see here. So you have here 5, right? So you have 5 here and 5 here. And so what happens is, I'll just move this up. Ah, come on. Sorry, I'm just trying to use the drawing tool. Okay. All right. So you basically have 5 minus 5 alpha 0. And then if you substitute in that formula, original function, you would get this expression here. And then it becomes 1 minus 5 lambda 0 and squared. So if you evaluate this function, you would get eventually something like 37.5 minus 50 lambda 0 plus 75 lambda 0 squared. And then you take the derivative of this, so it becomes 150. You take the partial derivative of that function here over lambda 0, and it's set equal to 0, and it becomes 150 lambda 0 minus 50. And if you solve for 0, it becomes lambda 0 equals to, you bring the other side 50, it becomes 50 over 150. And that's equal to 1 over 3. Right? That's the solution. That's the solution for lambda. Very simple, right? So nothing to it. So this is how you would get here this lambda 0, 1 over 3. So you basically take that expression of x0 minus lambda 0 gradient 0. So x0 minus lambda 0 gradient 0. and put the values in for each cell entry and substitute in here. Express these, take the first order derivative, set to 0, and solve it. Solve for alpha. Now you have minimized the alpha. You have found the alpha at which that expression becomes minimum. Exactly here. Say choose alpha to minimize the function at this point. So you want to substitute this whole expression, or alternatively minus alpha g here, alternatively like that, inside the initial function, and then evaluate this by taking the first order gradient, set it equal to 0, it will find the minimum. So this is how to minimize, right? Very much like you've done so far with other methods. And this is how you get alpha. Now you have alpha, you can calculate, go back here, and you can calculate the next step. Xk plus 1 equals to xk plus alpha. As now you know everything. You know alpha, you know s, you know x, right? So you can substitute those values, and if you evaluate it, you will see that it becomes just x0. So it's 5, 1 plus 1 over 3 times, what is s? S is, okay, so it's plus 5, 5. So it's 5, 5. So you basically, sorry, it becomes, you can do it by, let me see. Yeah, it becomes, let's say, minus 1, 3 over g times g. So you will see this is what you get, 3.33 and minus 0.67. So this is what you will get for x1. It's very straightforward if you plug it in. And then you can compute the new gradient. Now you have x1, which is that next step, xk plus 1. First you had k equal to 0, so you have x0, now you have x1. So you have the gradient g1. Now you want to compute this bit here, this gradient here, this step. You evaluate it at this point. So this is the gradient, general expression is x1, 5x2. You plug in this new value, 3.3 here, and 0.667 into x2. So this becomes 5 times 0.667 negative, which is minus 3.333. So this is how you get this value here by just simply substituting these values into the gradient. You get now G1. Now you have G1, you have X1, you have alpha 0. What you want to do next is to compute beta. This was this part here. You have G, you have X, now beta. Now what is beta? So beta is G1 transpose times G over G0 transpose times G0. So if you plug in G1 transpose, so which is this one here, G1 transpose it, so this becomes horizontal vector multiplied by G1, by this one, and then divide that result by G0 transpose G0. You have G0 here, you transpose it, and you divide, and then you multiply by itself in the previous form, vertical form. So just the G transpose G. And if you do calculation, you will see that you will get 0.444. So you get a number. So this beta 1 now is the new, gives us a new search direction by using the formula from before. If you remember, we had now next step is calculate the new search direction, sk plus 1, which is this formula here. You go here. So the new search direction S1 is negative G1 plus beta 1 S0. So 1, 1 here, 0 here, just like here, 1, 1, 1, and previous original guess of S0. And you substitute. So G1 is negative G1, is this, plus 0.44 times S0, or yeah. And then you basically will get this. So once you have this new S1, now you have everything, and now you want to go back to this point here to calculate alpha 1, just like I've shown you before. You now substitute these values, so x1 minus alpha 1 times G1. You substitute into here, take the first order derivative, set to 0, find the next alpha 1, and you will see that it comes out to be 0.6. So that would be the basically the next step. But I guess it says here that it comes to the exact solution at origin. As you evaluate this, you will see that actually already reached the solution. So even CG now reached the solution in 1 or 2 steps only, just like the Newton's method. If you check it, you'll see that actually it found the minimum. But yeah, so basically, yeah, this is the example. All you have to do basically is to find what you need, what ingredients you need at each step of the way, such as, for example, initial guess, gradient at the initial guess, search direction is just the negative of gradient. Then you choose alpha to minimize these. So you can find alpha by, as I just shown you by hand, how you can do so by substituting original function, the expression of x plus. You can also, what I do is x minus alpha kg. So I put g back here myself normally, but this is yeah, this is expressed here for convenience later, as you can see here. So this can be expressed much easier. But anyway, so this is what I do. I plug it in, calculate it as I show it by hand, find the next x, find the next g, find the beta, and then find the s. So x, g, beta, s. Now you have everything, and you keep stepping until you converge. So that's the procedure of this algorithm, and shown here. Okay, so to move on, so we can finish this last method for this next lecture. Today's lecture is the Gauss-Newton method. And it's basically used to fit models to data. So it's using nonlinear least squares method. Let's say you have lots of samples or measurements of a reaction rate, and these are the red dots. So you want to find a mathematical model which can closely represent those measurements so that you can actually find them at any point in time, let's say 2.1. So you know what it would be at this point, or later on, maybe at 10 seconds later. So it could be anywhere. So to be able to fit certain measurements to a model, to a mathematical formulation, we can use for exponential functions, as I will show you here. Let's say you have certain measurements at different time points, let's say 0 seconds, 1 second, 2, 3, etc. And the measurements are 2, 0.7, 0.3, 0.1, right? So these are the measurements. And you want to fit these measurements to some expression. And let's say we want to choose an expression which is a mathematical model which it's expressed in terms of x1 and x2. And it's exponential formulation. So it's x1 times exponential x2 times t. And so basically we want to fit this to this, or that to that. So either way, you look at it. So basically, given data ti, yi, so this multiple I goes from 1 to n, find vector x or x1, x2. Basically, this is a vector containing elements x1 and x2, 2 parameters. So this is why it's called multidimensional. It's got 2 values, or maybe 3 or 4 or something. And that gives us the best fit in least square sense to model function ftx, where f is a nonlinear function of x. So it's a nonlinear function containing exponential, right? So basically, we want to fit this data now. So in that sense, we have to define a component of residual. So to judge, we want to judge how closely are we in our model from our model. So this is our model function, tix. It's a function of these 2 parameters as you saw before with t and x, right? This is a model function. If we subtract our value at our model function from the measurement, and if it's equal to 0, that means we have a really good match, perfect match. So we don't have to do anything. Our residual, what's left over, is 0, and that's great. This is what we want. But in reality, this is not the case. In reality, it's going to be some sort of value, how far we are off. That if you remember here, how far are we? We might be off by some amount. So we want to minimize that distance. We want to minimize the sum of these distances between the measurement and our model function as much as possible. And to express that mathematically is by taking the sum of those residuals and squaring it. The reason we often square it, from what I understand, is that if this is a negative or positive number, right, depending on if we are below or under this curve, we square it to make it positive, so that when we sum it up, we get one single value. So if you sum positive and negatives, you eventually maybe get a 0, and that's not going to be realistic. You might have, for example, very large distance from here to here, and also another one like very low from here to here, but very large, but very, very far away in negative sense. So you have a very large negative number, a very large positive number, and it will give you also 0, but it's not going to tell you anything. It's going to trick you. So what you want to do is you want to sum it and square it. That way you always maximize find the maximum difference. Now you're summing it up in positive sense. And this 1/2 factor here, so if you have 1/2, it's just mathematical convenience. It does not change anything in terms of objective function. We want to still minimize this expression. But what it does, it later on, when we do some sort of derivatives and such, it will simplify some maths later on. So this is a little convenience expression to mathematically introduce. It's nothing much than that, that's all. It does not mean anything apart from some simplification for maths later on. But otherwise, this is the main form here. So we want to sum square it. And this is also expressed in some sort of matrix formula or vector formulation, also with these two double brackets, this summation factor here, and it's called L2 norm. So it's got a 2 and the denominator, and you have this is square, so because square here. This is called L2 norm, and it's basically sum of squares. That's what it is. So if we want to write this in a matrix form, okay, so we want to say we have this 1/2 and then this sum. Now this sum we can actually also express as multiplication of two vectors. The same vector R, transpose it and multiply by R. So this will become the inner product, or the first. So it's going to be by itself, multiplication by itself, which is just squaring. So this will be squared. But this works because vector transpose times the same vector will give you, a value. So otherwise, if you just have R times R, it's not going to do anything. It doesn't work. So it has to be transpose here. So this now is a mathematical expression equivalent to this form, right? And if you take the gradient of this function, let's say we call this now phi. This expression, we call this phi, this one here. And we take the gradient of phi, and if you express it, if you take the gradient of, let's say, RT, this part here, so basically you bring in the partial derivative into this expression. You will basically see that it's going to be partial derivative of R transpose X times Rx. And what is the partial derivative of R transpose? It's just one dimension, sorry, first order gradient. It's first order gradient, which we called G previously, remember G. But here we call it J. Now this is what's called Jacobian. Jacobian is always referred to as the first order gradient. I guess we should have maybe not called it G at the very beginning of this lecture, but J instead. It would be the proper way to call it. So this would be the first order gradient, Jacobian, transpose times R. So this is the expression. And I can show you in the next few slides. And normally, I guess these lectures don't go into details in this regard sometimes we omit these two slides, but I will try to go through them so you can just briefly see and then continue on with the rest of it. So how to get the second order gradient, so the derivative of this. So the gradient of the gradient, second order gradient or Hessian, it will become this formulation here. So eventually you have to apply product rule, as I will show you next. So let's see how this is done. So Jacobian is just that, as I just said, is the partial derivatives of Rj or Xj, Xi, where J can be from 1 to m and I can be from 1 to n. And in this case, I think we just have, so we have R1 to Rm. Okay, so, and if we have, let's say two, so this would be the expression equivalent to it. And if we have the gradient of a multivariable function, which is a vector consisting of partial derivatives. So let's say we have a gradient at x1, x2, so just partial derivative of that in terms of x1 and partial derivative of the function in terms of x2. So this is this expression here. This is just Jacobian. So, okay, so this is the slide, you know, Professor Feng typically doesn't go into great detail to explain, but I'll just try to briefly go through here. So we saw that this d phi, right? So where are we? This one here. This is what it is, right? So it's just the gradient of that. This should be, I think, transpose here, by the way. I had to check, but this should be, yeah, the gradient of one term times the other one. You get Jacobian made a vector transpose R, and because this is the Jacobian, so this should be a T here, I believe. I will check later on and fix it if necessary. Okay, but anyway, this is the expression for the first order, and the second order will be taking derivative of that first order, which happens to be product rule. So you have to keep this one here fixed, and you take the gradient of this one, and the gradient of that one is just the gradient of that one. Just so introduce your gradient operator here, and this one remains fixed. So there should be a T here, I believe. Okay, I could be wrong, but I'm pretty sure. Okay, I'm pretty sure there should be a T here. I will check with the cross coordinator, but I know it's a T. So this should be like that, right? And then we sum it, and so then we have to keep this term here fixed, and then we take the gradient of this term. So it becomes, this one is fixed, there you go, it's fixed, and then the second term is just squared because we're taking it second time. So now we have taken the product rule on these two ones. This is similar if you, let's say, have we have x1 e minus x1. All right, something like that. So if you take the derivative of this function, you have to take it 2 times, right? So first time you keep this fixed, and then take the derivative of that, and then plus you keep this fixed, and then take the derivative of that, right? So it's called product rule in differentiation. This is high school maths, if you remember. And this is the same thing here for matrices and vectors. Same thing applies with product rule. So eventually what you see is you get this form, Jacobian transpose times the Jacobian plus this form here, Rj grad second order gradient Rj. So this is Hessian. We know that because it's second order. And this is the Hessian matrix here. And this is how we derived this expression here, how it was derived. Let me go back. I'll just clear the drawings. How it was derived here, this part. So J transpose J, and this part here, right? This is exactly this form. This is it, right? So this is H. Now, what's important to realize is if you remember previously, we had Hessian matrix at point xk and times sk, which is a vector, equals to a negative gradient of f. This was from previous method, if you remember, we derived. What's important to now see is if we substitute this H, this one here, this is our full expression, right? You plug it in here, this whole bracket times sk is equal to, what is the gradient of phi, which is just this part here. Sorry, this part here. This part here is just J transpose R. Here we go, negative, because negative sign here, J transpose R. So this is the expression, right? So now, as you can see here, first order Jacobians, these are first order gradients, simple to compute. Second order gradient, Hessian, difficult to compute, and again, easy to compute, again, Jacobian, first order gradients. Now, this difficult part, we ideally want to get rid of it if we can. So how to do that? One way to realize this is that in practice, not always, but often these residuals will be small. And when they are small, you can actually approximate this expression by making this negligible. So this falls out. This is not considered anymore because these residuals do not contribute much to the overall expression. This dominant factor, this one here is typically dominant. Not always, as we will see, but frequently. And therefore, we can linearize this problem. This is non-linear in a way, if you can think of it. But this will become linearized because now we can remove that. And we are now treating this non-linear problem of exponential function, as we saw previously, right? Being that model function to model this whole procedure of fitting, we minimize it by converting it to some sort of linear expression. And this is easy to solve, right? So what we do here is just that. We assume this is very small, and it often is. So what we are left with is just this term here, equals times xk equals to right-hand side, which is shown here, right? This is just rewritten again and put in yellow box so you can nicely see. Now, if you look at left side, right side, we have Jacobian transpose. We can just simply drop them because you can cancel them. Being on each side, they cancel out, right? You're left with just this part and rk, sorry, r of xk. And this is the form. This is the main formulation which we derived just now. And this is what we want. And the way to solve this, if you imagine Ax equal to B, matrix, so actually it's a vector, right? So actually it's like a formulation of basically n by 2 matrix. Actually, it's in this case, it have x1 and x2. So it's going to be only two columns from what I understand. So it's going to be not a vector, it's going to be like a matrix. It's a rectangular matrix. It's not square, but it's still a matrix system. So we're still solving it. And one way to do so could be by QR factorization, as you will study the next set of lectures over the coming weeks. Or we can do it some other way, as I'll show you later on, using pseudo inverse, as we will hopefully study shortly. And then we can then find the next step. So the next step would be previous original guess or previous step plus sk. So this would be the other part which we need alongside this expression, this bit here, which is always used, right? So, okay, let's see an example in action. So let's say use this Gauss-Newton method to fit nonlinear model function, which is ftx, which is what we want to fit, right? So x1 exponential x2t, this is what we start with as our kind of like a model to try. We want to use these. And this is the data as before, right? So you have 0.7, it's that little drop we saw at the start of the slides. These are the values of the data. So let's say we calculate first the Jacobian for each of these values of x parameters, x1 and x2. So these Jacobians are just partial derivatives of Ri, right, of x over dx, in this case 1. So it's a Jacobian of ij. So we have I, number of rows, depends on number of sample points. So these are rows. How many samples do you have? We have 4 samples. So we have 4 rows in our Jacobian. And we have here 2 parameters, x1 and x2. So we have 2 columns. So as you will see later, there will be 4 by 2 matrix, okay? But in this case, this 4 by 2 matrix, which we will get, as you will see next, now we can find the general expression for it. So if we take the partial derivative of that function, of this function, sorry, of y, our measurement y, right? This is our measurement yi. I can be 1, 2, 3, or 4, y, and then little index I, subindex I, minus this function here, our model function. This is our residual. So we are taking the partial derivative of this here, of y minus ftx. So what is partial derivative of y in terms of x1? It's 0, right? So this falls off. We don't have anything. What's the partial derivative of this expression in terms of x1? Okay, let's have a look. So we have x1, right? So if you take partial derivative of this, there's no x1 here. This is like a scalar, so nothing here to see, really. So if you take partial derivative of x1, it just, this stays like a scalar. This is like a, a. This could be like a or something. So you just that, exponential x2 ti. We keep the ti here because this is our sample points. And we have a negative sign. That's because of this negative here. It's no negative here, but we have it from our expression of r equals y minus f of tx. So negatives there, for sure. And then also here, x2, right? In terms of the x2 value, what is the partial derivative of this in terms of x2? Well, it's just take the inner partial derivative, so it just becomes ti in front, and x1 is rewritten, so it's x1 ti exponential of the expression itself inside. If you high school maths, this is it, right? So also negative. Okay, so now we have those two values, in terms of x1 and x2, and let's say we have some initial guess at, let's say we take 0.10, and we want to then Gauss-Newton step S0 is given by the linear least square problem as such. So how do we derive these? I will show you in the next slide the exact derivation of this metric system. What we have here, if you remember, if I go back, is this Jacobian times S equal negative R and this is it. Jacobian times S0 equal to negative R of that point X. Okay, so how do we get this matrix here and this vector here? And let's see in the next slide, and then I'll come back to this slide. This is the solution to it. So if you compute this is the solution you will get. And we won't go into details to compute it, but this will be, I guess, linear algebra part in the coming lectures in the next weeks, but this is the solution. And then, of course, you can calculate x1 equals to x0 plus s0, your next step. Then plug it in back again, your next step, and keep repeating the until convergence. Okay, so how do we get this one here? So here we have this Jacobian, as we said before, and this is expressed in terms of partial derivatives of R1 over in terms of x1, and R1 in terms of x2, R2 in terms of x1, R2 in terms of x2, R3 in terms of x1, R3 in terms of etc. So as you can see, we have here measurement 1, measurements 2, for measurements 3, measurements 4 measurements, right? And 2 unknowns, x1, x2, as in the model function. Those are the two. Those are these two here, right? x1, x2. In terms of those. So this is Jacobian. It's a 4 by 2 matrix now. As we derived just before, this here is showing you these steps are just orally explained. Here is how you derive these two forms is also expressed here. And we have, of course, our R equals y minus f of tx, And our measurements in this box here are just put here for convenience so we can recall what they are. So we can see, okay, those are the ones, okay. So if you plug in all your derivatives here, R1, X1, etc., you will see you will have, for the first one is minus X1, T1, because we have row I, so this becomes T1, and then it's also T1 here. This is the second derivative, so you can see it here in terms of X2. So these are the X2 column X2. This would be X3. If there was X3, there would be X3 here, X4. But now we have only a 2, X1, X2. So you can plug those in, and let's substitute. Let's put our measurements inside those two expressions we just derived. We plug in T1. What is T1? Okay, 0. Plug 0 times what is X1? Who cares, right? Because 0 times, let's see, X1. Yeah, X1 would be what we want to derive. But anyway, so it's going to be 0. In this case, it's 0. And what we have is just e to the 0, right? So we have e to the 0. And that's that. Because 0 times anything is 0. So we don't care what this is at the moment. So what is here? We have X1 times T1 e to the X1 T1. So we again plug in the T1, T2, T3, etc. inside these values. And we also have evaluate basically like those other values. When you plug them in, you will see that this becomes the expression. So you get basically here, eventually you get -1, -1, -1, -1, because this is just e to the 0. This is 1. Once you substitute values here, you will get this. So it becomes 0, -1, -2, -3, etc. Okay, so this is then basically, yeah, it's just basically that. So you get this matrix, and you also have your other matrix R. So this one here, was this one here. To compute the matrix R, you have, where are we? Okay, here. So it's, recall it, it's at the y, so basically y minus f of xt, right? So measurement y1, what was it? So it was here 2, 0.7, 0.3, 0.1. So you have different values for it, minus this function here valued at point x1, x0. So we took the guess, say x0 here, right? So it's got 1 and 0, and we plugged it here. This was 1, 1, 1, because x1 is 1, right? X1 is 1. So this term here is 1. So this is the term here. It's 1, 1, 1, and there was 0 here. This is the second term. We had here 0. Yeah, that's what it was. So we have 0 here and 0 here. So x2 is this term here, is 0. This is x2. We plug it here, it's 0. So this is how you get those scalars. And same here, you have x0, which is 0, and you have t1, which is 0. x0 is 0. Sorry, x0 is a vector with 2 values, sorry. But anyway, this would be it. So you have measurement 2, 0.7, 0.3, 0.1. Those are the measurements, right? Minus this expression here for the function. So the function was, what was it? This one, x1 exp x2t, right? We have the function x1 exp x2t. You plug in your x1, x2 values. x1 is 1, x2 is 0, our initial guess. You plug it in with t1. There you go, 1 and 0 and t1. You get this. You get 2 minus 1 times e to the 0. So this is 0. 1 times e to, again, because x2 is 0, everything is 0. You have this 2 minus 1, 0.7 minus 1, etc. You can see now you're getting -1, minus 0.3, positive 0.3, 0.7, and 0.9. So this is the derivation of it. So you get here this vector negative r is just that. So you go back, this is it. Your negative r is basically that. And where do we get negative r? Yes, we got this from here, there, right? We have negative r, it's negative on the other side. So now we have this form, we solve it using matrix calculation algebra, we get this solution, we find the next step, which is S0 plus X0, this plus that. So what would be? It would be 1 plus 0.69, 0 plus negative 0.61. It would be 1.69 and negative 0.61. So this x1 would be 1.69 negative 0.61. Okay, and this is shown here. So if we have the initial guess 1, 0, if you now take all the residuals, you calculate them, y minus f tx, if you remember. So your residual formula, you calculate them and you square them and sum them, you will get 2.39. If you then find the next step, as I showed you here, it would be 1.69 negative 0.6. There you go, 1.69 negative 0.61, as we said. And you find the residual, it will be sum of squares, it would be 0.212. And then you keep going. You take this this is your new value. You want to find the next one. You then do the same procedure again and again. And usually this is done on a computer. So then you have to do this by hand. It would be crazy in practice, of course. You have a job one day or your company and you want to calculate this, you use a computer, of course, right? But now you understand the theory and what's going on. This is the important bit. And so eventually you will see that these values become same, not that converging. It's not changing anymore, which means you can now stop. And this would be roughly good enough for you to say, yep, I found my solution. It's approximately 1.995, negative 1.010, or close to it. And I think this is satisfied maybe my problem solution. And this would be the pseudo or the algorithm pseudocode. So how you step. Let me see how far we've gone. Okay, maybe I'll continue a little bit longer now to show you some past assignment or past exam examples of where you, for example, you can maybe check for yourself, maybe do a little bit of computing by hand at home later. You can see, for example, if you have a population P of some small community in the outskirts of the city, which grows rapidly over a 20-year period, and you have some data points, this would be your function, measurements P and T. This is like Y previously, and you want to model it in terms of this model function. You have a bit more complicated model function. You can then step the same way, do the same thing all over again, but now you have a bigger matrix. You have 1, 2, 3, 4, 5, 6, 7 measurements, and 1, 2, 3, 4 unknowns. So you have a 7×4 Jacobian, right? So it's going to be a bit larger matrix, much larger. And of course, you wouldn't do this in exam. It's going to take you whole exam to finish computing 7×4 matrix. But maybe an assignment, you have much more time. This is for practice purposes useful, right? So, and the procedure, how to step, and just shown here. So Jacobian x0 times s0 is minus rx x0. This is how you would tell how you would do it. It's x1, next step is x0 plus s0. Then again, Jacobian x1, s1, etc. So very straightforward stepping. So the Gauss-Newton method replaces the nonlinear least squares problem by a sequence of linear least square problems, because we negated that Hessian second order term, because we said residuals are small. Let's negate it. Jacobian term was larger, so let's leave just that. But sometimes in practice, it can happen that the second order term is also dominant to some degree. It's not that negligible, and maybe your solution doesn't converge. So sometimes you may have to take into account the second order term and do that full expression, and that can be more computation intensive, but necessary sometimes. So if you have large residuals. So this slide just says that if the second order term is not negligible, we have to, it may not converge or may converge slowly, and you may have to take into account that Hessian component. If you remember, I'll go back, this one. You may take into this account, then you can't reduce this to this form. This is a simple form, linearized, right? you might have to do the whole expression, the whole thing, and compute it. And you can do so, of course, on a computer, right? You feed the computer what it wants to output, and this can be all computed, of course. But it's going to take a little bit longer for computer to go through the computations. Okay, so this concludes that, and I can finish, I guess, this one, Levenberg-Merkur method, which is basically saying that it's an alternative to the Gauss-Newton approximation. This specialized form called Levenberg-Merkur, LM, sometimes called LM. It's a special form, and it's got also a linear system. It does not take the Hessian into account, that second order term, but it does do a little trick where it takes a scalar parameter mu k and multiplies it by an additive matrix such that it changes the diagonal elements of this expression here to some degree such that it makes this expression more robust and better for convergence. It's still linear. It doesn't compute second order terms, but it may help you find a solution by doing this preconditioning. This is called preconditioning or regularizing this matrix system. And it's a little trick that's done. And usually this parameter can be chosen like by experience, or by, let's say, if you're running some problem and you can see how it's converging if you plug in different value. So you can go back 2.356, or could be like 2.78 or 3.15. You try different values, you can see how it's converging. Sometimes you might be able to optimize this parameter a bit more, even more advanced maths and such. But usually you can do so as long as it can converge to something suitable. And so this is one of the methods which can have this parameter, one value, which can be chosen to optimize your solution better without having to take the Hessian second order derivatives and such. Okay, so I think I have some more slides to show you and examples which I can talk to. I guess I can do a little bit of that. So, all right, so in the past exams, there were some questions regarding this, writing down the pseudocode for steepest descent algorithm, which is, it gives you 3 marks, so you can go back to your lectures, remember how Professor Feng Liu explained the steepest descent. You can do it here, explain why the line search is typically used, and so on and so on. I won't go into details, but you can have a look a little bit what to kind of expect, to kind of understand how to formulate answers in exam questions and such. So yeah, so this is basically the distance to the next point, and the gradient of that function tell you the direction to travel, which way to go and how far, steepest descent method. You might have some questions, something like this, where you have this expression from, as we just saw before, calculating Gauss-Newton or Newton's method, etc. And you can do some derivations of the first order gradient, second order gradient of some function. You can basically have a look at this yourself in spare time just to have some idea what to kind of expect from exams and such. If you have any questions, any problems, if you're stuck taking these examples, to check them by yourself, you can check with the tutor during the tutorial, or you can ask some of the lecturers how this, what can be done. But usually it's very straightforward, just like as you've seen before. You follow the steps and you practice it. And some more here, for example, you have some sort of 2x2 matrix and another matrix, and it's asking you to maybe do sort of steepest descent calculation and to show it on a graph. How, so if you do one steepest descent direction and distance, and you get new point, and then you have to draw a next point. So you might get some sort of graph. Maybe you might get a graph or something where you show 1 or 2 steps, how you step through search space to the global minimum, and using the formulation from steepest descent, this one here, alpha minus gradient of f plus initial guess, and so on. So, okay, I'll briefly introduce what some examples could be. Let's say you have an MRI system, And this MRI system consists, let's say, of superconducting magnets cooled to, let's say, 4 Kelvin, which is close to absolute zero. They produce a very uniform static magnetic field, which does not vary in time. It's static. It means it's always on. And you plug in your power supply. This cranks up to certain voltage and current. Because it's superconducting, there is no resistance in these coils. And eventually you can just remove your power supply and current will still circulate at that temperature. But usually the current is maintained by having a little bit of voltage given to it, but by specialized power supply. So eventually you get a static field. You also have then some sort of, and you have to optimize these superconducting structure. You have to optimize the size of the blocks, distance away from each other, how much current is passing through, forces between the elements, and have an objective function to do computation, let's say optimization of a uniform field in the center. And you want to create a very uniform field, maybe like 5 parts per million uniform in flux change in the center of the imaging region to get a really good signal. Otherwise, you won't see anything in the MRI image as such. This is how MRI creates a uniform, beautiful image, let's say with sub-millimeter resolution. This is a 7 Tesla image. This field is very strong, 7 Tesla. Normal in hospital, you would see like 1.5 Tesla, maybe 3 Tesla, but 7 Tesla is not commercially maybe approved yet. It's still used in research settings. So for example, we have one 7 Tesla system in the University of Queensland, and we have facilities probably number 1 in the Southern Hemisphere, or not sure if Melbourne is still competing with us. I have no track record of it, probably, but yeah, it's one of the top facilities in Australia from UQ, having 7 Tesla whole body system costing like $15 million or something like that, and other systems like for high field. So you have also then some sort of gradient coils, and these gradient coils, as you will see next, are very complicated structures of current carrying loops. And they create gradients through space. And these gradients are changing magnetic fields which change linearly in space in 3 directions, like X direction, Y, and Z. They're changing linearly, and they have to be uniform linearly changing. And they have to, and this is to encode, to find the position of the signal from any point in space. That's what they used. And for that purpose, 2 guys who came up with this, I think Lauterbur and Sir Peter Mansfield from Nottingham University, they created this system in '73, this Fourier-based encoding using gradient coils, and they have Nobel Prize obtained, I think, 2003, just like less than 20 years ago. And you also have radio frequency coils, which are antennas operating in megahertz. So you have DC, you have gradient coils, which are kilohertz, and you have radio frequency coils operating in resonance of that spin. It's using quantum physics basically to encode the position of signals from water molecules. Specifically, it's looking for protons in hydrogen atoms of water molecules. So these nuclei of hydrogen atoms in H2O. So it's looking for those which happens to be 70% of the body being water, which is great, gives a great signal. And this is what this is looking for. And this happened to resonate the magnetizations of this nuclei at a certain frequency, which is proportional to field strength at DC. So it happens to be like 64 megahertz, 128 megahertz for higher field systems and so on. And then, yeah, so this is how you can get nice images and even temporal images of heart in, for example, having right and left ventricle, you can see it in time domain as well. So you can image in time domain and space domain, 3D, 4D, and even multi-dimensional, like functional imaging. I'm not sure if you have some examples, but here's a green set, Z coil, like a Goulet coil transfers saddle, kind of like other Helmholtz and Goulet coils and such. You have different arrangements to compute, to get these 3 different gradients, which will give you slices of the anatomy in axial, sagittal, and coronal view. So this is what these gradients are for. They usually look like this, something like that. So very complex structures Not sure, like, yeah, so they have very complicated structures of current Kane loops. You have to optimize those using Gauss-Newton method, conjugate gradient or something like that. And you can also have secondary loops outside, for example, which you have to also optimize. And these happen to be, for example, to shield the system so there's no leakage field. So the field does not exist outside, so it's very minimal. Otherwise, the superconducting magnet can quench and explode if these fields happen to hit the superconductor outside, which is sitting outside. It will stop being resistive because these eddy currents from this will heat it up and it will quench, it will stop superconducting, and there will be explosion in the room. Can happen, has happened in the past in hospitals, for example. So I will continue with some of these examples till next time on Wednesday and show you some some real world optimization problems and continue with linear least squares. I'm going to stop here. I'm sorry. I think at the next lecture, and I just want to give you a bit more of a broad view. Thank you so much for being with me here today. I hope you have a nice week, and I hope the microphone now works better. Any questions, let me know. Okay, so thanks again for your patience. Thank you as well. Thanks, guys. Okay, I was born in Bosnia, which is former ex-Yugoslavia. Someone's asking me where I'm from. Yeah, so yeah, I came to Australia something like 20 years ago. I still have an accent because I came when I was something like a young adult. So I still have an accent. I could not remove it. Yes, ex-Yugoslavia, former, that structure which collapsed in the 90s. That's why I was born, and I lived in Germany, then came here. So yeah, so I was kind of around since ever there was little conflicts there and stuff. But yeah, so I think I've been with UQ for something like 20 years now. So as undergrad, postgrad, and also as a lecturer. I lectured something else. I think MRI. I lectured for 5 years before, but now I'm doing this as well and doing some research at university, I don't know, like robotics and also microwave imaging and some sort of things with maybe MRI a little bit, but mostly also I think I'm doing a little bit now solar nano antennas, like researching like a small scale, so like VLSI designs of stuff like that. Yeah, it's Sarajevo. It's capital, Sarajevo, capital of that part there of Bosnia. Thank you. So I guess thanks guys for your questions. It's between Austria, opposite of Italy. It's in the Balkan region, so it's got it's like a small country now, probably like 4 million people, I guess. I don't know, 2 million, 4 million, something like that. Used to be 22 million only, like for Yugoslavia. But it was, I think, interesting place to be in the past. I lived there until I was probably like 11 or 12. And I got some culture to understand, like, that culture a little bit as a child. But yeah. Thanks again. Hope you are getting some grasp of this material, which is for some people not maybe immediately kind of like understandable, but as you look through examples, you will see that it's not really that too much to it, and you can probably learn very easily. And by some examples, you can practice it. I think practice is important, so you can understand the steps. Okay, thanks as well. Hope you enjoy your week too. Okay, all right. Have a good week, guys. Bye. I mean, guys and girls. I say guys because that's colloquial in Australia, like saying, "Oh, hey." Okay, see you all. Thank you, everyone.